We mentioned that inclusion and exclusion principle is very useful too, and it could help us to solve many combinatorics problems. Now let's review some problems that we've encountered before to see whether IEP could provide a new method to solve them. For example, let's say we are very familiar with indeterminate equations. For instance, x1 plus x2 plus x3 is equal to some constant. We ask the number of its non-negative roots. We know that we use the bar method to solve it, and we could also use the formula say n plus b minus 1b to solve it. For example, in this expression, if the right-hand side is equal to 15, the answer is c 3 plus 15 minus 1, 15. It seems that we already know how to do this problem, but what if I add a condition? For instance, if for every xi, it has a specific domain, how should we deal with this? In the previous problem, if I add the following condition, the domain of x1 is 0 to 5, the domains of x2 and x3 are both ranged from one integer to another integer. Now, it seems that the formula say n plus 1 minus 1b no longer works, because it might contain solution sets in which x1 is larger than 5. What should we do now? Could we use the IEP solution instead? So let's think that for this problem, we need to focus on these limitations. For example, x1 has to be in 0 to 5, x2 has to be in 0 to 6, and x3 must be in 0 to 7. If we simply ignore all these limitations, the problem is the same as the old one, which is a number of non-negative roots for equation like x1 plus x2 until xn equal to 6. And we could simplify using c n plus 1 minus 1b directly. So now we should think that with these new restrictions, what we need to think is how to exclude the arrangements which violate the restriction. Let's do a detailed analysis. For the situation without any restriction, we could solve the number of non-negative roots of x1 plus x2 plus x3 equal to 15. It's say 15 plus 3 minus 1, 15, which is equal to say 17, 2. Then for the arrangement which violates the restriction, we will discover that if an arrangement violates the restriction, one situation is that x1, which is larger or equal to 6. Assume x1 is larger or equal to 6. Substitute it back in the equation, it means that this variable is larger than 6. So could we do the substitution here? Suppose that A1 contains the solution sets in which x1 is no less than 6. Now we substitute x1 with y1 plus 6, y1 plus 6 plus x2 plus x3 equal to 15. Move 6 to the right hand side and we transform the equation to y1 plus x2 plus x3 equal to 9. For this equation, we could use c n plus b minus 1b directly. We could calculate the size of A1. It's c 9 plus 7 minus 1, 9 equal to say 11, 2. This is how we deal with the first condition. Similarly, we do the same thing for the second restriction. For the second restriction, if it's violated, it implies that in this situation, x2 is no less than 7. Similarly, we could still let A2 denote the set of solution set in which x2 is larger or equal to 7. Now we use y2 plus 7 to substitute x2. x1 plus y2 plus x3 should be 15 minus 7. The number of its non-negative integer solution is c8 plus 3 minus 1, 8 equal to c10, 2. Similarly, for the third restriction, x3 is in 0 to 7. If we violate this restriction, it means that x3 is no less than 8. So as we did, we let A3 to be the set of solution set in which x3 is larger or equal to 8. x1 plus x2 plus y3 plus 1 equal to 15. After analyzing, the size of A3 is say 7 plus 7 minus 1, 7 equal to c 9, 2. So we define three different sets. Then what do we want to calculate? We want to get the number of solution sets which obey the restriction. For those who don't violate x1 is no larger than 5, they are complement of A1. For this, we also require it to obey the corresponding restriction, which is A2 complement. For the third restriction, we also require it not to be violated. So it's A3 complement. As we want all of them to be obeyed, we are calculating the intersection of them. So our answer is supposed to be A1 complement intersect with A2 complement intersect with A3 complement. As we could also solve the sizes of A1, A2, and A3, of course we could also do the similar thing to A1 intersect with A2, A1 intersect with A3, etc. Then we just use the IEP to deliver our wanted result. Let's keep analyzing. As we want to solve the number of non-negative roots with such restriction, we could calculate that A1 size equal to C 11.2, the size of A2 equal to C 10.2, A3 equal to C 9.2. A2 intersected with A3 means that we violate the first restriction, so that x1 must be larger or equal to 6 here. For the second restriction, it is also violated. X2 should be larger or equal to 7. So it means that y1 plus 6 plus y2 plus 7 plus x3 is equal to 15. Now we could find that the intersection of A1 and A2 is C2 plus 3 minus 1, 2 equal to C4, 2. Similarly, we could calculate A1 intersect with A3, A2 intersect with A3. Well, A1 and A2 and A3 means that the first violation is which is larger or equal to 6. The second variable is larger or equal to 7. The third variable is larger or equal to 8. 6 plus 7 plus 8 has been larger than the right hand side, so the intersection between A1, A2, and A3 is 0. Now we need to calculate A1 complement intersect with A2 complement intersect with A3 complement and use it on the inclusion and exclusion principle. The size of universal set is C17.2 minus C11.2 minus C10.2 minus C9.2 plus C4.2. And then plus C31 plus 1 is 10. So this is number of non-negative roots with restriction, which is what we want.